Hello. In this video we're going to talk about something called correlation. Correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Linear correlation exists between two variables when there is a correlation and the plotted points of paired data results in a pattern that can be approximated by a straight line. So here we just have a bunch of examples of some scatter plots, and we're going to take a look at how to interpret those. So the very first example that we have here, we can see that these data are sort of clustered around a line. They're not exactly on a line, nor do we want them to be exactly on a line. We want there to be some variability in there. And we can also see that as we move from the left to the right, the data points are getting higher. This is what we would call a positive correlation. There's something called the correlation coefficient. It's denoted with a letter R. And for this particular scatter plot, the correlation coefficient R is equal to 0.851. The closer this value R is to 1, the more linear the correlation is, or the stronger the linear correlation is. So positive correlation means that it's going up and to the right. So as we move from the left to the right, the data values are getting higher, or these plotted points are going up. In this next graph, we have a negative correlation, because as we move from left to right, we can see all of these plotted points get lower and lower. Again, the data values are clustered around this line, but they're not all exactly on a line perfectly, which is, again, what we want. So with negative correlation, the R that we get will end up being negative. So the correlation coefficient R for this set of data is negative 0.965. Again, it's close to negative 1 here. So it can either be close to positive 1 if you have positive linear correlation, or negative 1 if you have negative linear correlation. So we can see in this graph that these data points are just all over the place. They're totally random, and they are not following the pattern of a line. And so here there is no correlation, and R is equal to 0 for this particular set of data. In the next example, so this data is not random and all over the place. It has this nice pattern, but it's definitely not a linear pattern. So this data is falling along a quadratic or a parabola shape, and so this does not have a linear correlation, and we can see that the correlation coefficient is far away from 1. It's pretty close to 0, in fact. So a R value, or a correlation coefficient that's close to 0, means that there is no linear correlation. The closer you are to either 1 or negative 1, the stronger the linear correlation. So that's the next topic, measuring the strength of the linear correlation. So some definitions. Linear correlation coefficient R measures the strength of the linear correlation between the paired quantitative x and y values in a sample. It is also known as the Pearson product moment correlation coefficient. Next, some notation. So again, R is the linear correlation coefficient for sample data. This is a Greek letter called rho, and it's the linear correlation coefficient for population of paired data. N is the number of pairs in your sample. The properties of the linear correlation coefficient are: the value of R is always between negative 1 and 1, and it's including negative 1 and 1. If all values of either variable are converted to a different scale, the value of R does not change. So we could change from inches to feet, and it won't change what R is. The value of R is not affected by the choice of X or Y, so we could interchange them. R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. So like the example that we had where it followed a quadratic or a parabola, that had a linear correlation coefficient that was really close to 0, stating that there was no correlation, but this is to measure linear correlation and not other types of correlation. R is also very sensitive to outliers in the sense that a single outlier can very dramatically affect its value. So here is the formula for R. If you thought that computing a standard deviation was bad, well, this is a little bit worse. So don't get overwhelmed by this formula. I am going to go through one example where we calculate this by hand, but I will never expect you to do it by hand on your own. So if you're going to be calculating R with your calculator, you would press on Stat, Edit, and enter your data into L1 and L2. Press Stat again and select Tests using the LinReg test, and this will give you several displayed values, including the linear correlation coefficient R and a p-value for a test to see whether or not there is linear correlation, and we'll go through that in a future video. You can obtain a scatter plot. You would press second and then y equals. Press enter twice to turn the plot on. Then select the first graph type, which represents a scatter plot, and then press zoom and select zoom stat and then enter, and you will get a scatter plot on your graphing calculator. If you're going to be using StatCrunch, these are the steps that you would follow. You can also get R if you have a scientific calculator. In this example, we're going to actually go ahead and compute the correlation coefficient R for the shoe print data and someone's height. And so we need to fill in this table. We need the sum of our x's, the sum of our y's. We need to square x's and then sum those. Square the y's and then sum those. We need to multiply x and y together and then sum that column. And then we'll plug it into our formula for R. So I'm going to go ahead and fill in this table, and then we'll come back and plug our values into R and compute what that is. And while I'm filling in my table, you might want to just pause the video and fill in the table for yourself, and then do it along with me. Okay, so here I have the table all filled in. So the first column is just taking this first column, x squared, is just squaring each of these x values. The next column over is just each of these values squared. And then this last column here is the first column times the second column. And then we need to sum up every single column in our table. So those are the values along the bottom, are the sums of each of the columns. Now I need to fill in this equation for R. So we have n times the sum of x times y. N is the number of pairs that we have, and we have 5 pairs. So that would be 5. And then the sum of x times y is this last number here. So that's 26,649.69. And then minus the sum of the x's. That's 150.2. And then times the sum of the y's. That's 886.5. And then we're going to divide that by the square root of 5 times the sum of the x squareds. So here's the sum of the x squareds. That's 4,523.14 minus the sum of the x's squared. So that would be 150.2 squared. And then times the square root of n, which is 5, times the sum of the y squareds. So that's this big number here, 157,271.47, and then minus the sum of the y squared. So that's 886.5 squared. So compute the numerator first, and you can just type it in just as it is. 5 times 26,649.69 minus 150.2 times 886.5. Hit enter, and then divided by, and make sure that you put parentheses around this entire denominator. So once you do that, you should get 0.591. So this is a lot of numbers to type into your calculator, so you do need to be extremely careful if you're going to do this. And again, I'm only doing this here to show you how it's done. You'll always just enter in your data and then click a few buttons and your calculator will do this computation for you behind the scenes. I just wanted you to see one time where this number is coming from and how it gets calculated. So that's it for this video. I hope you're having a terrific day. Let me know if you have any questions.